In this video, we continue our discussion on models for chemical bonding, focusing on covalent bonds and bond energies associated with covalent bonds. Here's an important figure that we need to understand. This is a representation of the hydrogen system where we're forming a covalent bond between two hydrogen atoms. Let's start looking at this figure on the top of the panel up in the upper right-hand corner. We see the number 1. That represents the first state of the hydrogen system. We have two black dots. Each black dot represents a hydrogen nucleus. The blue shading around it represents the electron cloud distribution. So we have one proton and one electron approaching another proton with its electron. As we move to state 2, the atoms have now moved close. So the atoms are moving in a straight line towards one another. As they get closer, you can see the shading on the electron cloud begins to shift between the two nuclei, because the electrons are now attracted not just to one nucleus, but to two. So we see electron sharing is beginning. When we reach state 3, we've fully formed our covalent bond. Now we see our two hydrogen nuclei, and the dark blue shaded region between the two nuclei represents the electron distribution. That electron distribution is what is the formation of a covalent bond. Now when we get to state 4, when the atoms are coming together, if the two nuclei get too close, they'll repel one another because the positive charges repel and they push away from each other. Now we can look at the graphical representation of this system. On the y-axis is potential energy, and this is the potential energy for the two hydrogen atom system. The x-axis represents the distance between the two nuclei. Let's first look at the black line at potential energy equal to 0. So at the top of the graph, that represents 0 potential energy. So that's the energy of the hydrogen atoms at very large distances. When the hydrogen atoms are far apart from one another, we define the energy of this system as 0. Now we give the atoms just a gentle push, and as they move towards one another, we can see from the red curve that the atoms begin attracting one another, particularly when you get closer than about 200 picometers. So the atoms are attracting one another, and it's similar to the cation-anion attraction, like in a crystal lattice, but it's a much more muted. It's a weaker interaction because they're not full charges. So we see the electrons begin to move between the two nuclei. So what happens to the potential energy of this system? It goes down as the two atoms get closer. The potential energy drops. But since the total energy of the system is constant, then the kinetic energy has to be increasing. So the kinetic energy of the system is the difference between the 0 line and the red curve. So we can see the atoms get closer and closer together, and then when we hit state 3, this is the minimum in this potential well. So this is the minimum in the curve. That minimum represents the most stable state, the minimum potential energy. And the energy for that system for hydrogen is negative 432 kilojoules per mole. That's what we term the bond energy for the system. This is the bond energy for a hydrogen molecule. And when you're at that minimum, the distance corresponds to 74 picometers. This is what we call the bond length. So you can see the thick yellow arrow on the right side going upwards shows the energy that has to be absorbed by a hydrogen molecule when it's in its stable state in order to dissociate. So that's called the bond energy, or sometimes called the bond dissociation energy. In this text, or in your Silverberg text and in this course, we'll generally just use the phrase bond energy. Now, if the nuclei get too close, they'll repel one another, push back apart, and they can fly apart. Normally, when you have a hydrogen molecule in a stable state, it sits at the bottom of the potential well. On the lower right-hand region, we see our final part of this figure that we're going to look at. And this is the representation of the hydrogen molecule in its most stable state. So we see the two black dots with the plus in the middle represent the two protons in the system, the two hydrogen nuclei, and the two yellow circles with the minuses in them represent the two electrons. You can see that the electrons then tend to reside between the two nuclei. Now, of course, we know from chapter 7 that electrons as well as protons are waves. So their positions are not fixed and defined like particles. They're wave functions. And so this is only an artist's representation showing that the electrons tend to spend time between the two nuclei. That's what causes covalent bond formation. The electrons residing between the nuclei to minimize their potential. Here we look at the hydrogen system in a little bit different way. We're looking at the distribution of electron density around the two nuclei. Before we look at these figures, remember back to chapter 7. We would look at an individual hydrogen atom, and we had graphs that showed the probability density function, or the probability of an electron being distributed around the nucleus at various locations. We had spherical distributions for the 1s, the dumbbell shapes for the 2p, for example. And if we had the 2s, there would be nested shells. There would be two concentric circles for electron density. So now let's look at the hydrogen molecule. And the hydrogen molecule we're looking at is in its ground state. And let's look at panel A first. The dark spots in the center represent the hydrogen nuclei, and the concentric ellipses represent electron densities at constant density around the two nuclei. You can see the darker regions are areas where there's higher electron density, and the lighter regions are where there's less electron density. There's the highest electron density around each nucleus, but there's also substantial electron density between the two nuclei. In panel B, we can see a side-on picture of this, kind of a topographic map. And you can see the peaks in electron density at the nuclei, but you also see very large, substantial electron density between the two nuclei. So we see that covalent bonding involves shared electrons moving between the nuclei to minimize their energy and maximize stability. That's what holds together covalent bonds. Now, these are complex diagrams that we've looked at. We can look at simpler pictures, and this is what we'll generally use and what you'll use throughout this course and when you move on to organic chemistry. Generally, atoms share electrons to achieve a full outer level of electrons, as we've seen. The shared electrons are called a shared pair, or most commonly called a bonding pair. So for hydrogen, we have two electrons between the two nuclei. We can represent this with two dots, or we can represent it with a single line. That single line is the more common representation and the one we'll use in the rest of this course. That line represents a single bond, a pair of electrons holding together two nuclei. That's the covalent bond. An outer electron pair that is not involved in bonding is called a lone pair, or sometimes an unshared pair. So the lone pair could be envisioned, for example, in the fluorine molecule, F2. The fluorine molecule has one single bonding pair, so it has a single bond. But you know that fluorine atoms each have 7 valence electrons. 1 electron was shared. The other 6 electrons go into lone pairs. bond order is the number of electron pairs being shared by a given pair of atoms. A single bond involves one bonding pair. That would be one that would have a bond order of 1. So if we have 2 electrons between 2 nuclei, the 2 electrons pair together, and that pair is called a single bond. There are cases where we'll have 4 electrons between 2 nuclei, and those will gather together in 2 bonding pairs to form 2 bonds, or what we call a double bond, and that has a bond order of 2. When we have 6 electrons involved in bonding, then they would form up into pairs. We would have 3 bonding pairs. That's a triple bond, and a triple bond is identified as having a bond order of 3. The bond energy is the energy needed to overcome the attraction between the nuclei and the shared electrons. That's that energy that holds the 2 nuclei together, like we saw in our potential energy well a couple of slides before. We have to put in enough energy to break that bond. That's called the bond energy. The stronger the bond, the higher the bond energy. The bond length is the distance between the nuclei of the bonded atoms. It's tempting to make some generalizations, and we're going to show a couple of panels from your textbook that talk about generalizations, but we're also going to talk about where these generalizations have significant shortcomings. For a given pair of atoms, a higher bond order generally results in a shorter bond length and a higher bond energy. That's for a fixed pair of atoms. For a fixed pair of atoms, for a given pair of atoms, a shorter bond is generally a stronger bond. Bond length tends to increase down a group in the periodic table and tends to decrease across the period. The bond energy tends to show the opposite trend. So we're looking at situations where small, as we go to the across a period, the size of the atom decreases, the atoms can get closer, and they tend to have stronger bonds. But that's a very, very general trend that is, and the opposite is observed a lot of times. So there are many exceptions to this trend, as we're going to see in a moment. Now, this table shows typical bond energies and typical bond lengths. These are average values. The ones that are correct values, specific correct values, would be for the diatomics. So, for example, in the upper left-hand corner, hydrogen bonding to hydrogen, fluorine, chlorine, bromine, and iodine, those are diatomic molecules, and those are the correct bond energies and bond lengths. And in the lower right-hand region of the upper part of the figure, above the line, you see the halogens and the interhalogens. Those are all diatomic molecules, and those are all correct bond energies and bond lengths. So, for example, now if we go again to the left-hand side of the table, in the left-hand column, and go down to carbon bonded to hydrogen, C-H, there are literally tens of millions of known carbon-hydrogen bonds, all having different energies and different lengths. In fact, the large majority don't have known energies because they've not been measured, and they don't have known lengths because they've not been measured. But these are typical values. They can vary by plus or minus 20% or more. Now, typically, when you have a single bond, like the carbon-carbon single bond, 347, down below you'll see the carbon-carbon double bond, 614. That's a typical sort of behavior. The carbon-carbon single bonds are more than half as strong as the carbon-carbon double bonds. So the carbon-carbon double bonds are not twice as strong as the carbon-carbon single bonds. And that's usually the case for other sorts of bonds like carbon-oxygen, carbon-nitrogen, carbon-carbon. The double bonds are not more not twice as strong. They're a little bit less than twice as strong. And we'll see why that's the case when we get to chapter 11. Note that fluorine to halogen bond strength, bond length correlation, which is interesting. It does show that the bond strength decreases down this period, but the bond length is also increasing. So bond lengths can increase and bond energies can increase, or they can decrease. So the most important thing are measured values. Now here's a review of bond length and its relationship to covalent radius, as we talked about back in chapter 9. We know what the internuclear distance is. We can measure those values. So then the covalent radius is identified as 1/2 of the internuclear distance. And here this is shown for all 4 halogens: fluorine, chlorine, bromine, and iodine. This table shows approximate relations of bond order, bond length, and bond energy. You can see generally as the number of bonds increases, of course the bond order goes up, the average bond length tends to become shorter, and the average bond energy goes up. As it says at the bottom, double bonds have bond energies that generally are less than twice the strength of single bonds. And triple bonds, their bond energies are also typically less than 3 times the bond energy for single bonds. Now, there are forces within a molecule, and those forces within a molecule are covalent bonds, but there are also forces between molecules, and these are what are called intermolecular forces. They're shown here in this chapter, but we're not going to discuss them here. We will go through intermolecular forces when we come to chapter 12. Here we see there are an interesting case of certain solids, notably quartz and diamond, but there are others like this. They're what we call network covalent solids. So we often think of solids as being ionic compounds, but there are solids for elements like carbon. They can be either graphite or diamond. And in this case, the bonds between the atoms are covalent bonds. And these materials are often very hard and have very high melting points. And you can see something similar for silicon, bonding to oxygen. This is what's in quartz or sand. And there are covalent bonds in this system as well. Next, we're going to tie together bond energies to something we learned earlier. That is the standard enthalpy for a reaction. The heat released or absorbed during a chemical change can be thought of as being due to the difference between the bond energies of the reactants and the products. So it takes energy to break bonds apart, but then you regain energy when new bonds are formed. And so the lower equation is one that you will use. The upper equation is more of a conceptual equation, but the lower equation shows the enthalpy, standard enthalpy for a reaction is equal to the sum of all the bond energies of the reactants that are broken minus the sum of all the bond energies for the products that are formed. So this is an important equation, and we will use this equation in our later video when we go through mechanics. This is a correct, exact equation, and it's useful in a number of applications. Here's a way to visualize this. So Silberberg has given us a nice figure that shows us why you take reactants minus products. Of course, you think back and you say, when we did enthalpy, standard enthalpy for reaction, we took the enthalpies of the products minus the enthalpies of the reactants. Why, in this case, are we taking the bond energies of the reactants minus the bond energies of the products. And this figure shows why. We start off with two diatomic reactants. We can have an intermediate where we break everything up into atoms. And in order to do that, we have to put energy into the bonds. So we'll break the two bonds. So we break the hydrogen bond, we'll break the fluorine bond. Breaking the hydrogen bond requires 432 kilojoules per mole. Breaking the fluorine bond requires 159 kilojoules per mole. So here we're adding up the bond energies of the reactants. But then when we form the products, we drop downhill by forming two hydrogen fluoride molecules. So now we take the hydrogen fluoride bond energy, that is 565 kilojoules per mole. There are two of those, so we multiply this by 2. And that's the energy we regain. Thus, the net standard enthalpy for the reaction is the energy it took to break up the reactants minus the energy we regain from forming our products. Silberberg has expanded this, and he shows us an example: methane reacting with oxygen to form CO2 and water. And there are carbon with 4 hydrogens around it, so you can break it up into atoms. And then we reform the oxygen, and this forms our carbon dioxide and water. And conceptually, this is a very useful figure. We have to be very careful with the numbers, though, because the calculated enthalpy, standard enthalpy for this reaction is incorrect. And there are two major flaws in this approach, and you should be aware of this and just understand that if you avoid the flaws and use the equation correctly, in the future you will always get the correct answer. So where's the issue here? What are the two major flaws? While that equation is strictly correct, first, not all 4 carbon-hydrogen bonds have the same bond strength when they're broken. And you might think, well, they're all carbon-hydrogen bonds, aren't they equal? Yes, they are, except when you break the first one, now the second one will be harder to remove because the electrons have rearranged. Pulling off the third will be even harder, and the fourth will be even more difficult. Because when you break off the carbon-hydrogen bonds, they come off one at a time. And as they come off, the remaining carbon-hydrogen bonds change their strength. Additionally, the data in table 9.2, just like we talked about before, are averages for many systems except the diatomics in that table. So the numbers aren't the true bond energies for carbon, hydrogen, CH4. So you don't get the correct value. If you go and do it using the methods in chapter 6, which are correct, you'll get a different number. So if you are kind of really diligent and careful, you may compare those and you'll see differences. Now let's think about this from the perspective of fuels. This is something that's important and useful for majors who are in nutrition and dietetics. And this is also important for those who are involved in aerospace and mechanical engineering thinking about fuels. Because we know that if I have a material and I'm going to burn it and get carbon dioxide and water, what sort of material do I want to use? Do I want something with strong bonds or with weak bonds? Well, remember, if we go back to our equation up above, we take the bond energy of the reactants minus the bond energy of the products. The bond energy of the products may already be fixed, and so let's take two different situations. Let's take an alkane versus an alcohol. Alkanes would be, for example, common gasoline, and then alcohols would be, for example, when ethanol is added to the gasoline. So you can see the alkanes tend to have weaker bonds because the carbon-hydrogen bonds are weaker than the carbon-oxygen bonds. Therefore, for the alkanes, the bond energy of the reactants is smaller than the bond energy of the reactants for the alcohols. So what does that tell us? Who gives us more energy, the alkane or the alcohol? Well, the alkane will, because it has weaker reactant bond energies. Another example of this related to food substances are a comparison of lipids and carbohydrates, or lipids are sometimes called fats. Fats have predominantly carbon-hydrogen bonds. Carbohydrates, or sugars, typically have carbon-oxygen bonds. That's why you get more energy from eating fats than you get from eating carbohydrates, because the reactant bond energies in fats are weaker than the carbon-oxygen bonds in the carbohydrates.